Let us discuss the Ostwald process. So this is an industrial method that is used for the large-scale production of nitric acid. Now, nitric acid is a very important component in the manufacture of fertilizers, explosives, and many other chemical products. Now, when it comes to this process, what I'm going to do is first I'm going to introduce the raw materials, talk about the optimum conditions for the process, and then dive into it. So what are the raw materials? We have three. Number one, ammonia. Ammonia is obtained from the Haber process, where nitrogen and hydrogen gas react together under certain conditions to form ammonia. We also have air and water. So these are the three raw materials. We also have three conditions that need to be there. These are the optimum conditions, the best conditions for the production of a high yield of nitric acid. Number one, the presence of a catalyst. So the catalyst that is used is an alloy of platinum rhodium. And that is the reason why it's written as such. So it's not platinum, it's not rhodium, it's an alloy of both. We have temperatures. The temperatures are usually between 700 degrees Celsius to 900 degrees Celsius. And lastly, pressures as high as 9 atmospheres. Let us start. So I'm going to divide all of the steps that happen into five main ones. Our first one is purification. So ammonia is initially mixed with air, excess air. Now this mixture of ammonia and air is the one that is purified. Now by doing so, you're going to have removal of impurities such as dust and carbon dioxide. These impurities, if they were left to remain where they are, they will end up poisoning the catalyst. So when we talk about the term poisoning of catalyst, what do we mean by that? So this is the process whereby you're going to have these impurities binding to the catalyst surface, attaching themselves onto the surface of the catalyst. Now, by doing so, they are going to reduce the effectiveness of the catalyst. This, of course, is going to reduce the catalytic activity, which in the end will lower the yield of nitric acid. You're not going to be able to get as much nitric acid as you could have gotten without the impurities. So purification gets rid of impurities which would otherwise have poisoned the catalyst. Now our next step is passing on to a compressor. Now the purified gases are passed into the compressor. Over here what happens is that they are going to be compressed zeta fino to a pressure as high as 9 atmospheres. This high pressure is very good because it actually favors the formation of the product. Our next step, you're going to have this mixture. Remember, the mixture is of ammonia and air being passed on to a heat exchanger where it's going to be warmed to temperatures as high as 230 degrees. Okay. Now, when you talk about a heat exchanger, what do I mean by this? So heat exchangers are devices that are used in industrial processes to recover and transfer heat from hot gases into the incoming gases. Okay, let me explain. In this process, we are going to have ammonia reacting with oxygen, which will lead to the production of a lot of heat because the process is exothermic. So what the heat exchanger does is that instead of wasting this heat, allowing it to be lost, it captures it from the hot gases. And then this heat is going to be used to preheat the incoming gases because the reactions are going to proceed faster when the temperatures are higher than normal. So you're going to have heat being produced, being captured, and then being used to warm the incoming gases. So by doing so, you're going to need very little external energy to maintain the high temperatures of the reaction, okay? So this of course increases the efficiency of the whole process, making it more economically viable. So in the heat exchanger, you're going to have the gases being preheated, okay? After this, they move on to the catalytic chamber. This is where the reactions take place. So you're going to have ammonia reacting with oxygen, leading to the formation of nitrogen 2 oxide and steam. Now, this reaction occurs at a temperature of between 700 degrees Celsius to 900 degrees Celsius. And of course, it occurs through the presence of a catalyst. So what the catalyst does is that it provides a surface for the reaction of ammonia and oxygen. Now, would this reaction have occurred without a catalyst? Yes, it can occur under normal conditions, but the reaction is very slow. So the catalyst speeds it up without being consumed. Now, this reaction is highly exothermic. It leads to the production of a lot of heat energy, which is very, very good because this heat energy that is produced helps to maintain the temperature that is needed without any further heating being done. Now, once this has taken place, the hot gases are then passed back through the heat exchanger. So they pass through the heat exchanger on their way to the catalytic chamber. And then on their way out of the catalytic chamber, they again pass through the heat exchanger. Now, on their way back, what happens is that they are going to be cooled. How does this happen? The heat exchanger absorbs any extra heat and then uses this to warm the incoming gases. The mix of gases then passes into the reaction chamber where you're going to have nitrogen 2 oxide reacting with oxygen present in the excess air. So this leads to the formation of a brown gas known as nitrogen 4 oxide. I want to say this. This reaction, the one that leads to the formation of NO2, is best carried out under low temperatures of around 45 degrees Celsius. But these are the temperatures that are going to be present in the reaction chamber because this mix of gases passed through the heat exchanger on their way out where they were cooled. Now, this reaction does not require anything, it's spontaneous. You have nitrogen 2 oxide, you have oxygen, you have low temperatures that favor the reaction, and voila, these two react and you get nitrogen 4 oxide. Now, once the nitrogen 4 oxide has been formed, it's mixed with air and then passed through an absorption tower. So this is going to be against a downward flow of water as such. So nitrogen 4 oxide is a very soluble gas. So it's going to dissolve in water to form two acids, nitric 5 acid and nitric 3 acid. Now nitric 5 acid is what we want, right? But nitric 3 acid is going to undergo a further reaction. So it's going to react with the oxygen present. Remember we talked about excess air being mixed with nitrogen 4 oxide. So it's going to react with the oxygen present in the air to form nitric 5 acid. So the purpose of the air being mixed with nitrogen 4 oxide is simply to ensure that the nitric 3 acid that was produced is oxidized to nitric 5 acid. Now the nitric 5 acid that is prepared this way is around 65% pure, but it can be made more concentrated through fractional distillation. And that brings us to the end of our lesson today.